Welcome back to Forged Under Pressure, the channel that tells the stories behind the machines, the unsung battles fought not with bullets, but with blueprints, slide rules, and sheer, stubborn persistence. We celebrate the finished product, the sleek fighter that dominates the skies, the engine that shatters speed records. We see the glory, the power, the seemingly inevitable march of progress. But innovation is rarely inevitable. It's often a brutal, bloody fight against inertia, against skepticism, against the experts who know all the reasons why something can't be done. It's a fight fought by individuals, often alone, armed with nothing but an idea and the courage to see it through, even when the world tells them they're wrong. Tonight, I want to take you back to a pivotal moment, a time when the jet age was dawning, full of incredible promise but also plagued by terrifying limitations. Engines were powerful but fragile, thirsty, prone to catastrophic failure. Pushing the boundaries meant flirting with disaster. The problem, as many saw it, was complex, requiring massive leaps in materials, science, in thermodynamics, in brute force engineering. But one engineer, a junior member of a team overshadowed by giants, saw a different path. A simpler path. An idea focused not on the fire, but on the flow. An idea for the very heart of the engine, the compressor, the turbine, the internal propellers that gave the jet its breath and its power. His design was elegant, it was efficient, and it was rejected, not once, but twice. Called impractical, structurally unsound, a deviation from proven principles. But that engineer refused to let it die. They rejected my propeller design twice. Now it's standard on every U.S. jet. Before we ignite this story, if you believe that perseverance is the true fuel of innovation, and that these often forgotten struggles deserve recognition, then I need you to join our flight crew. First, hit that subscribe button and make sure you engage the afterburner by ringing the notification bell. It guarantees you won't miss critical mission updates. Second, give this video a like. It provides the thrust we need to reach a wider audience. And finally, drop a comment down below. Let us know what country and city you're launching from. Seeing our global squadron assemble is always a powerful reminder of why we tell these stories. All right, checklist complete. Let's taxi to the runway. My name is Arthur Vance, and in 1949 I was a very small cog in the very large, very loud machine that was the Allison Engine Company's experimental jet division. Fresh out of MIT with a master's degree that felt increasingly theoretical in the face of roaring test stands and exploding turbine blades, I was assigned to the Compressor Aerodynamics Group for Project J71. The J71 was supposed to be Allison's masterpiece, America's answer to the powerful British axial flow jets, an engine destined for the next generation of fighters and bombers, planes still only existing as classified blueprints. It was a beast, a multi-stage axial compressor, cannular combustion chambers, a two-stage turbine, pushing the absolute limits of metallurgy, thermodynamics, and manufacturing capability. It was also a notorious flame-out queen, prone to compressor stalls, turbine failures, and generally behaving less like a precision machine and more like a barely contained explosion. My specific job under the august and intimidating Dr. Harold Ainsworth, head of compressor design, was Stage 3 stator efficiency analysis. It sounds impressive. It wasn't. It meant I spent my days staring at Schlieren photographs of airflow through static stator vane cascades in a wind tunnel, measuring boundary layer separation, calculating pressure ratios, and tweaking the vane angles by fractions of a degree, trying to eke out another 0.1% of efficiency, trying to delay the inevitable stall that plagued the high-pressure stages of the J71 compressor. Dr. Ainsworth was a legend, a pioneer who had helped design Allison's first centrifugal flow jets during the war. He was brilliant, meticulous, deeply conservative in his engineering philosophy, and utterly convinced that the path to jet engine perfection lay in incremental refinement of established principles. His world was one of precise calculations, known material limits, and rigorously tested. Conventional airfoil shapes for the compressor blades and stator vanes, shapes derived largely from subsonic propeller theory, just scaled down and spun much, much faster. The problem was, at the speeds the air was moving inside the later stages of the J71 compressor, approaching Mach 1 right on the blade surfaces, Those conventional shapes weren't just inefficient. They were becoming dangerous. The airflow wasn't behaving nicely anymore. Shock waves were forming. Tiny localized sonic booms that tripped the boundary layer, caused the airflow to separate, disrupted the pressure rise, and ultimately led to the catastrophic aerodynamic breakdown known as a compressor stall. Essentially, the engine choking on its own air, often resulting in a violent surge, a flameout, or worse, the engine tearing itself apart. Ainsworth's team attacked the problem with relentless, methodical refinement. They tweaked the blade angles. They adjusted the curvature. They experimented with slightly thinner profiles. They added vortex generators, tiny wing-like tabs designed to re-energize the boundary layer. They were polishing a cannonball, achieving tiny, hard-won gains, but never fundamentally solving the core issue, the shock waves. The air itself, at near sonic speeds, was fighting back against the shapes they were forcing it through. I, the junior analyst staring at Schlieren photos until my eyes burned, started seeing something different. Not just the stall, but the onset of the stall. I saw the tiny shock waves forming first, not on the main body of the blade, but right at the tips, especially near the leading edge, where the relative airflow velocity was highest. These tip shocks seemed to act like a trigger, propagating inwards, thickening the boundary layer, initiating the separation that cascaded into a full stall. It was analogous in my mind to the compressibility problems propeller designers were facing on aircraft, but happening inside the engine, on dozens, hundreds of tiny spinning propellers, the compressor blades themselves. The senior engineers knew about tip shocks, of course, but they treated them as an unavoidable consequence of high-speed rotation, something to be managed, mitigated, but not eliminated. Their focus was on the overall stage efficiency, the big picture. But what if the tip was the key? What if, instead of just accepting the tip shock, you could delay it, or weaken it? How? The conventional answer was, make the tip thinner. But we were already pushing the limits of structural integrity. Thinner blades meant weaker blades, more prone to vibration, fatigue, and catastrophic failure, especially with the primitive alloys we had back then. Ainsworth's conservatism was rooted in harsh reality. Engines did explode if you pushed the materials too far. Late one night, staring at a particularly frustrating Schlieren photo, showing a beautiful, strong shockwave blooming right off the leading edge tip of a stator vane, I had a thought so simple, so counterintuitive, it felt almost stupid. Everyone was focused on the profile of the airfoil, the cross-sectional shape. But what about the planform? The shape of the blade as viewed from above. All our compressor blades and stator vanes were essentially straight, rectangular, or slightly tapered, like miniature airplane wings, sticking straight out from the hub or the casing. The airflow hit the entire leading edge, from root to tip, at roughly the same time. What if you swept the blade, like the Germans were doing with their jet fighter wings? If you swept the leading edge back, the airflow wouldn't hit the entire edge simultaneously. It would encounter the blade root first, then progressively encounter sections further out towards the tip. More importantly, the component of the airflow velocity perpendicular to the leading edge, the component that primarily determines shockwave formation, would be reduced at any given point along the swept edge. You could trick the air. The blade tip, even though it was moving at near sonic speed, would feel a slower, effectively subsonic flow along its swept leading edge. The shockwave formation could be delayed, pushed to a higher rotational speed or a higher airflow velocity. The stall margin could be increased. Efficiency could be improved. It was the exact same principle Richard Whitcomb was simultaneously, secretly, exploring for transonic aircraft drag with his area rule fuselage shaping over at NACA Langley, though I wouldn't learn about his work for years. Such was the compartmentalization of research back then. Two different problems: external aircraft drag, internal compressor efficiency, potentially solved by the same elegant counterintuitive concept: sweep. My heart started hammering. It seemed too simple, too elegant. Why hadn't anyone else thought of this? Or had they, and dismissed it? I frantically started sketching on the back of a test data sheet, not airfoil profiles, but planforms. Compressor blades swept back like scimitars. Stator vanes curved gracefully against the direction of rotation. It looked right. It felt aerodynamically sound. But the structural implications, Ainsworth's ghost, loomed large. A straight blade experiences primarily centrifugal force pulling it outwards, and bending forces from the airflow pushing it backwards. Relatively simple stresses. A swept blade. The centrifugal force would now try to unsweep it, to straighten it out, creating complex twisting and bending moments. The aerodynamic forces would also act differently, potentially creating flutter or vibration modes we hadn't accounted for. Building a swept blade strong enough to survive the hellish environment inside a jet engine compressor, spinning at 10,000 RPM, subjected to incredible heat and pressure. It was a nightmare. A structural impossibility, perhaps. But the potential gain, if it worked, it wasn't just 0.1% efficiency. It could be 5%, 10%. It could fundamentally change the performance equation, allowing for higher pressure ratios per stage, meaning fewer stages, lighter engines, more thrust, better fuel efficiency. It could fix the J-71. I spent the next 2 weeks in a frenzy of covert calculation. I couldn't use the official computational resources. That would leave a trail. I worked late, using my slide rule, my log tables, and sheer brute force mathematical grit. I ran stress analyses, trying to estimate the twisting moments. I sketched mounting configurations, trying to figure out how to anchor a swept blade securely to the compressor disc. I even built a crude balsa wood model of a swept blade cascade and held it in the low-speed smoke tunnel just to visualize the flow, praying no one would ask what I was doing. The numbers were terrifying. The stresses were indeed significantly higher, more complex, but they weren't infinite. With the right root design, the right material, maybe one of the new titanium alloys the materials lab was playing with, the right internal reinforcement, it might be possible. Barely. It was a high-risk, high-reward proposition. Time to face the dragon. I requested a 15-minute slot at Dr. Ainsworth's weekly design review meeting. My heart was pounding like a trip hammer as I walked into that room, armed with my sketches, my hand-scrawled calculations, and a terrifyingly fragile conviction. Ainsworth sat at the head of the long table, flanked by his senior engineers, men who had decades of experience, men who had built the engines I was proposing to fundamentally change. The air was thick with the smell of pipe tobacco and intellectual certainty. "Mr. Vance," Ainsworth said, peering at me over his spectacles, his tone weary, already anticipating a waste of his valuable time. "The floor is yours, briefly, if you please." I put my first sketch on the overhead projector, a comparison of a straight compressor blade and my proposed swept design. I explained the concept, delaying tip shock through sweep, reducing the perpendicular velocity component. I showed my crude smoke tunnel photos, conveniently omitting the balsa wood nature of the model. I presented my efficiency gain estimates, the bold, almost unbelievable 5 to 10% numbers. For a moment there was silence. Not impressed silence, confused silence, like I had just started speaking in Martian. Then the question started, polite at first, then increasingly sharp. "Mr. Vance," one senior engineer began, "while the aerodynamic theory is intriguing, have you considered the centrifugal untwist moment? The stress concentrations at the root attachment? This blade would tear itself from the disc before you even reached idle speed. And the manufacturing complexity?" another added. "Forging or machining a blade with this complex three-dimensional curvature, with the tolerances required. It's simply not feasible with current technology. Furthermore," a third chimed in, "sweep induces spanwise flow, pushing the boundary layer towards the tip, which could increase tip leakage losses and potentially worsen the stall problem, not improve it. Have you accounted for that?" They were hitting all the right points, the points that had kept me awake at night. "I believe," I started, trying to keep my voice steady, "that with advanced titanium alloys and a redesigned fir tree root attachment, the structural loads can be managed. And while spanwise flow is a concern, the benefits of delaying the primary tip shock should outweigh." I never got to finish. Dr. Ainsworth held up a hand, silencing me. He hadn't asked a single question, just listened, his expression growing colder. harder. He slowly, deliberately tapped my sketch of the swept blade with his pen. "Mr. Vance," he said, his voice quiet, but carrying the unmistakable weight of absolute authority, "what you are proposing is not merely difficult, it is fundamentally unsound. You are suggesting we abandon decades of proven aerodynamic practice based on subsonic propeller theory, which has served us perfectly well, in favor of a radical, unproven geometry derived from, what, German wing designs? Smoke tunnels." He shook his head, a look of profound disappointment on his face. "You are ignoring the structural realities. You are ignoring the manufacturing limitations. You are ignoring secondary aerodynamic effects that could prove catastrophic. This sweep, it is a dead end. It offers a hypothetical, marginal gain in one area at the cost of catastrophic failure modes in 10 others." He pushed my sketches back towards me across the table. "This design is rejected, Mr. Vance, completely. I expect you to abandon this line of inquiry immediately and refocus your efforts on optimizing the Series 5 stator cascade profiles, as assigned. Do I make myself clear?" The finality was absolute. There was no discussion, no argument, just rejection. Utter, complete, soul-crushing rejection. My revolutionary idea, the key to fixing the J-71, the future of jet propulsion, was dead before it was even born. Dr. Ainsworth's rejection wasn't just a professional setback, it felt like a physical blow. Walking out of that design review, leaving my sketches, my solution, lying ignored on that polished table felt like abandoning a part of myself. The weight of his certainty, the collective dismissive agreement of the senior engineers, the sheer authority behind the rejection. It was suffocating. Fundamentally unsound. Dead end. Catastrophic failure modes. The words echoed, a chorus of condemnation designed to crush any lingering hope, any spark of defiance. For a few days, I was adrift. I went through the motions, dutifully running the endless, tedious cascade tests on the Series 5 stators, tweaking infinitesimal angles, measuring boundary layer thicknesses that felt utterly, cosmically irrelevant. What was the point of optimizing a fundamentally flawed system by fractions of a percent when the real breakthrough, the quantum leap, was being actively suppressed? The frustration was a constant, low-grade fever, simmering beneath a carefully maintained facade of professional compliance. I saw the J-71 prototypes continue to struggle on the test stands. I heard the hushed, anxious conversations about another failed high-altitude ignition test, another compressor surge that nearly ripped the engine off its mounts. Ainsworth and his team doubled down, convinced the solution lay in even tighter tolerances, even more precise fuel scheduling, even more complex bleed valve systems to manage the airflow, Band-Aids on a fundamentally hemorrhaging design. They were treating the symptoms, while I believed I held the cure. But what could I do? I was Arthur Vance, the junior nobody, the man whose radical idea had been publicly shot down by the Oracle himself. To bring it up again would be unthinkable, an act of sheer, career-destroying insubordination. Ainsworth had made his pronouncement. The case was closed. Trying to reopen it would be seen not as persistence, but as arrogance, as a refusal to accept the wisdom of my superiors. I'd be marked, permanently, as a troublemaker, an academic dreamer incapable of understanding practical engineering. My future at Allison, perhaps in the entire aerospace industry, would evaporate, yet I couldn't let it go. The image of those swept blades, the smooth, efficient flow I had visualized, the potential, it haunted me. Every time I heard the tortured scream of a J-71 compressor approaching its stall limit on the test stand, I felt a physical pang of guilt. "I know how to fix you," I wanted to yell at the roaring machine. But they won't let me. The injustice of it, the stupidity of clinging to dogma when a solution was within reach, gnawed at me. This wasn't just about proving myself right anymore. It was about the engine. It was about the pilots whose lives would depend on it. It was about winning the technological race against the Soviets, who were undoubtedly facing the same aerodynamic challenges. Letting this idea die felt irresponsible. It felt like a betrayal, So I did what engineers do when faced with an immovable object. I started looking for cracks. I couldn't attack Ainsworth's authority head-on. But maybe I could gather more data, irrefutable data, data that even he couldn't dismiss. My initial calculations, my hand-drawn graphs, my balsa wood smoke visualization, they were preliminary, easily attacked as unsound. I needed rigorous proof. I needed computational fluid dynamics, CFD simulations, something that was still in its absolute infancy, requiring massive amounts of mainframe computer time. I needed detailed finite element analysis, FEA, to prove that a swept blade could be designed to withstand the stresses. And, most importantly, I needed hardware. I needed to build and test a real, metal, swept blade cascade in a high-speed wind tunnel to show unequivocally the aerodynamic benefits. All of this was impossible. CFD and FEA time was reserved for top priority projects, allocated by Ainsworth's own managers. Wind tunnel time was even scarcer, booked months in advance, and fabricating experimental complex geometry titanium blades. That required machine shop access, materials requisitions, funding, all things utterly beyond my reach. I was checkmated again, unless I got creative. My official work on the Series 5 stators became my shield, my camouflage. I stretched the analysis out, justifying the need for more detailed boundary layer measurements, requiring more wind tunnel time, albeit in the low-speed tunnel, which was less in demand. And while the tunnel was running, supposedly gathering data on stator wakes, I started experimenting, discreetly. I couldn't test a full swept blade, not yet, but I could test elements of the theory. I could introduce small amounts of leading-edge sweep near the tip of a conventional stator vane, disguising it as an anti-erosion modification. I could subtly reshape the leading-edge radius, trying to replicate the effective thinning effect of sweep. I worked closely with the wind tunnel technicians, older guys, hourly workers mostly, who had seen engineers like Ainsworth come and go, and who often had a healthy skepticism towards the pronouncements from the front office. I learned their language, shared coffee with them, listened to their complaints about the demanding schedules. And sometimes late at night, when the official tests were done, they might forget to turn off the tunnel for an extra 15 minutes. 15 minutes was all I needed to swap in a subtly modified vane, run the smoke generator, and snap a few precious illicit Schlieren photographs under slightly higher flow conditions that hinted at the transonic regime. The photos were grainy, inconclusive on their own, but they showed something. A slight weakening of the tip shock wave on the modified vanes, a delay in the boundary layer separation. It wasn't definitive proof, but it was fuel. It kept the fire burning. The computational side was harder. Mainframe access was tightly controlled, but I discovered a loophole: the university partnership program. Allison had a collaborative agreement with Purdue, my alma mater, allowing limited access to their newer, more powerful mainframe for educational research. Officially, I was supposed to be mentoring graduate students, analyzing non-proprietary aerodynamic data. Unofficially, late at night, dialing in via a noisy modem line from my apartment, I was running my own code. I taught myself Fortran. I coded rudimentary CFD models, simplified, two-dimensional simulations of the flow around my swept airfoil shapes. The simulations took days to run, churning through punch cards, spitting out reams of printed numbers that I would frantically analyze before the university sysadmins noticed the unusually high CPU usage. Again, the results were crude, limited by the available computing power and my own developing skills. But they corroborated the theory. They showed a clear reduction in wave drag, a significant increase in the stall angle of attack compared to the conventional blades. The FEA problem was the toughest. Stress analysis of complex shapes required specialized software that Allison guarded jealously. But here, luck intervened. A new engineer, fresh out of Stanford, was hired into the turbine design group, a different kingdom, far from Ainsworth's compressor fiefdom. This young engineer, David Chen, was an FEA whiz kid, tasked with analyzing turbine blade cooling channels. He was also ambitious, slightly starstruck by the Allison legends, but also frustrated by the rigid hierarchy. We met awkwardly at a company picnic. I cautiously, vaguely described my structural challenge, analyzing complex stresses in a nonlinear rotating component. Chen's eyes lit up. He saw it as an interesting theoretical problem, a chance to show off his skills outside his assigned plumbing job. He didn't ask what the component was. He didn't need to. He just saw the math. He agreed, unofficially, to run some FEA models for me, after hours, disguising them as turbine blade root stress studies. I gave him the geometry, the material properties, hypothetical titanium alloy, the rotational speeds, the aerodynamic loads derived from my CFD runs. A week later, Chen handed me a thin folder, his face a mixture of excitement and confusion. "Art," he said, "this shape of yours, it's bizarre. The stresses are insane. Way higher than any conventional blade." But he opened the folder. Inside were color-coded stress contour plots, beautiful complex images generated by the FEA software. If you use that high-strength Ti6L 4V alloy, and if you thicken the root section just so, he pointed to a specific area on the plot, and maybe add an internal reinforcing spar here. Theoretically, it holds. It's right on the ragged edge of the material limits, probably zero fatigue life, but it doesn't actually fly apart in the simulation. It holds. The words hit me like a physical force. My structurally unsound design, the one Ainsworth had dismissed out of hand, it was possible. Difficult, yes. Expensive, undoubtedly. Pushing the limits of known metallurgy? Absolutely, but possible. I now had the trifecta: preliminary wind tunnel data hinting at aerodynamic benefit, CFD simulations confirming the drag reduction, and FEA results suggesting structural feasibility. It wasn't definitive proof. It wasn't a finished design, but it was evidence. Hard, quantifiable evidence that directly contradicted Ainsworth's expert pronouncement. Now what? Confront him again? Wave Chen's FEA plots in his face? That still felt like suicide. Ainsworth wasn't a man who admitted error gracefully, especially not when challenged by a junior subordinate armed with data obtained through questionable means. I needed a different angle. I needed a crisis he couldn't solve, a situation where his methods were visibly failing, creating an opening for a radical alternative. The J71 itself provided the opening. As the program moved towards pre-production prototypes, the stall problem wasn't getting better. It was getting worse. The engine could barely reach its design pressure ratio before surging violently. Test pilots flying the early prototypes in experimental aircraft reported terrifying flameouts at high altitude and high G loads. The Air Force, which had bet heavily on the J71, was getting nervous. Rumors started circulating about program reviews, budget cuts, even cancellation in favor of rival engines from GE or Pratt & Whitney. Ainsworth was under immense pressure. His methodical, incremental approach wasn't working. His team was running out of tweaks, out of ideas. The atmosphere in the compressor group became thick with anxiety, frustration, and hushed, desperate arguments. This was my moment, not for a direct confrontation, but for a subtle, carefully placed suggestion. Through back channels, through sympathetic engineers and other groups who were aware of my swept blade theory, the rumors had spread despite Ainsworth's rejection. I started leaking, not classified data, but the concept. I'd casually mention the potential benefits of sweep in conversations with turbine designers. I'd leave printouts of my CFD results, carefully anonymized, accidentally on a table in the cafeteria. I shared my FEA findings, again presented hypothetically, with engineers in the materials lab. I was planting seeds, creating a low-level buzz, letting the idea of swept compressor blades percolate through the engineering grapevine, positioning it not as my rejected fantasy, but as a potential, albeit radical, solution to the J71's very public, very expensive problems. I knew it was a long shot, but I hoped that if enough other engineers started asking questions, started wondering what if, maybe, just maybe, the pressure would build on Ainsworth from the sides, not just from below. Maybe the program management, desperate for any solution, would start looking beyond Ainsworth's conservative inner circle. It was a dangerous game. If Ainsworth discovered I was deliberately circumventing his authority, spreading my rejected theory behind his back, he would crush me. But doing nothing felt even more dangerous. The J-71 was dying, and I held the key to potentially saving it. I just needed someone with the power and the courage to finally use it. My guerrilla campaign of whispers and accidentally placed data printouts was a desperate, almost pathetic strategy against the institutional fortress of Dr. Ainsworth's authority. For weeks, it felt like throwing pebbles against a dam. The J-71 program continued its slow-motion death spiral. Test Stand D, where the latest prototype, Engine 007, was undergoing high-altitude simulation runs, became a place engineers actively avoided. The compressor surges were becoming more violent, the flameouts more frequent. One particularly bad surge event resulted in catastrophic turbine failure, sending red-hot blades punching through the engine casing and embedding themselves in the reinforced concrete walls of the test cell like shrapnel. Miraculously, no one was killed, but the incident sent a shockwave of fear and recrimination through the entire program. The Air Force liaison officer, a grim-faced Colonel Baker who seemed permanently attached to Ainsworth's hip, was practically living in the control room, his reports back to Wright-Patterson becoming increasingly dire. The rumors weren't just about budget cuts anymore. They were about outright cancellation, about Allison losing the most lucrative and prestigious engine contract in a generation. Ainsworth himself became a ghost, rarely seen outside his office or the closed-door crisis meetings. When he did emerge, he looked pale, drawn, the weight of the potential failure etched onto his face. His legendary certainty, his absolute conviction in the correctness of his approach, seemed shaken. He was a brilliant man, trapped by his own success, his own history, unable or unwilling to see beyond the incremental refinements that had always worked before. But this problem was different. This was the wall of transonic airflow, and polishing the cannonball wasn't working anymore. Then, slowly, almost imperceptibly, the seeds I had planted began to sprout. An engineer from the turbine group, the section responsible for the other end of the engine, stopped me in the hallway. "Vance," he said, looking around cautiously, "that CFD stuff you were running, the stuff about managing shockwaves with geometry, you think that could apply to turbine inlet guide vanes too? We're seeing some nasty choke points at high pressure ratios." I feigned ignorance, talked vaguely about theoretical possibilities, but the conversation itself was a small victory. They were thinking about it. A week later, a manager from the manufacturing division cornered me in the cafeteria. "Art," he began, using my first name for the first time. "Hypothetically, if someone were to design a compressor blade with, say, a complex nonlinear three-dimensional curvature, could we even make it? With our current 5-axis mills? What kind of tolerances are we talking?" Again, I played dumb, discussed general manufacturing challenges, but the dam was starting to crack. The idea of sweep, my radical, rejected heresy, was starting to circulate, fueled by the program's desperation. People were looking for any alternative, any life raft, as the J-71 Titanic continued to take on water. The real shift came during a tense all-hands program review meeting, mandated by a nervous Air Force. Ainsworth presented his team's latest fixes, minor tweaks to bleed valve schedules, subtle reshaping of the problematic Stage 3 stators. The data showed marginal, almost negligible improvements. The stall margin was still dangerously thin. Colonel Baker looked unimpressed, his expression bordering on hostile. The room was thick with the unspoken fear of failure. Then, during the Q&A session, a hand went up in the back. It wasn't me, it was Henry Wallace, the chief project engineer for the entire J-71 program, Ainsworth's boss's boss, a man known for his pragmatism and his brutal honesty. "Harold," Wallace said, his voice calm but carrying immense weight, "these refinements are admirable, but the core problem remains. We are hitting an aerodynamic wall. Are we absolutely certain, that there are no alternative aerodynamic configurations worth exploring, even unconventional ones?" All eyes turned to Ainsworth. It was a direct challenge, delivered politely but unmistakably. Wallace knew about my theory. The grapevine had reached him. He was giving Ainsworth one last chance to embrace the unconventional, or be bypassed. Ainsworth stood at the podium, his face pale, his hands gripping the edges. He looked trapped. He could double down, defend his failing approach, and risk Wallace overriding him. Or he could acknowledge the possibility, however remote, however humiliating, that a junior engineer's unsound idea might hold the key. He took a slow breath. "Henry," Ainsworth began, his voice strained. "As you know, we explored several radical configurations early in the design phase. Concepts involving significant geometric deviations were deemed structurally infeasible or aerodynamically counterproductive due to secondary flow effects." He paused, choosing his next words carefully. "However, given the persistent challenges, perhaps a limited, theoretical re-evaluation of certain novel, aerodynamic shaping concepts purely as a risk mitigation exercise might be prudent." It wasn't an endorsement, it wasn't an apology, but it was an opening. A crack in the dam, just wide enough for me to slip through. Within 24 hours, I was temporarily reassigned. No longer under Ainsworth's direct command, I was assigned to a newly formed Compressor Aerodynamic Improvement Task Force, reporting directly to Wallace's office. My official mandate was vague. Explore advanced aerodynamic concepts for potential future engine designs. My unofficial mandate, conveyed by Wallace in a brief, intense, closed-door meeting, was crystal clear. "Vance, that swept blade thing of yours, you have 6 weeks. Build it, test it, prove it works, or bury it forever. Your budget is whatever you need. Your authority is me. Just don't fail." It was the chance I had been waiting for, praying for. But the pressure was immense. 6 weeks to go from theory, from illicit tests and simulations, to a fully functional high-speed cascade test that could definitively prove the concept, under the intense scrutiny of the entire skeptical organization. Failure now wouldn't just mean exile. It would mean the final, irreversible death of my idea, and potentially the J-71 program itself. I practically lived in the high-speed wind tunnel complex. With Wallace's top cover, I had unlimited priority. I pulled in David Chen, the FEA whiz kid who had proven the structural feasibility, assigning him to finalize the blade route design. I worked hand in glove with the best machinists in Allison's experimental fabrication shop, men who initially scoffed at the bizarre, twisted shape, but whose professional pride kicked in as they tackled the immense challenge of milling titanium into a form no one had ever successfully created before. We weren't just building blades. We were inventing the process to build them as we went. We built a single-stage test rig, a full-scale cascade of my swept stator vanes, designed to replicate the conditions in the critical third stage of the J-71 compressor. The day of the first test run was terrifying. Ainsworth was there, standing silently in the back of the control room, his arms crossed, his face unreadable. Colonel Baker was there, looking impatient. Wallace paced nervously, chewing on an unlit cigar. The tunnel spooled up, the familiar roar building to a deafening shriek as the airflow approached Mach 0. 9, then Mach 0. 95, right at the inlet guide vanes. On the monitors, the Schlieren imaging came alive. We watched, holding our breath, as the airflow entered the cascade. With the conventional stators, the shock waves would be blooming now, the boundary layer thickening, the flow starting to separate near the tips. But with my swept vanes, the flow stayed attached, clean, smooth. The tip shock wave was gone. Not just weakened, but seemingly eliminated, pushed beyond the operating speed of the test rig. The pressure rise across the stage wasn't just stable. It was higher than the conventional design, significantly higher. And the stall margin, we pushed the back pressure, deliberately trying to choke the airflow, trying to force a stall, and it wouldn't break. It just kept working, stable, efficient, breathing, far beyond the point where the conventional stage would have violently surged. The numbers on the screen were undeniable. A 15% increase in stage pressure ratio, a 30% increase in stall margin. It wasn't just better, it was a different universe of performance. The control room was silent. Wallace slowly took the unlit cigar from his mouth, a look of stunned disbelief transforming into a wide, slow grin. Colonel Baker just stared at the numbers, shaking his head. And Ainsworth stood frozen for a long moment, his face pale. Then, without a word, he turned and walked out of the control room. It wasn't a walk of anger or defeat. It felt more like surrender. He knew. His era was over. The future had arrived, and it was swept. The rest is, as they say, history. The J-71 program was saved. Swept blades, refined and integrated not just into the stators but the rotor stages as well. A whole new set of structural challenges masterfully overcome by engineers building on my initial breakthrough became the core of the redesigned compressor. The engine finally met and exceeded its performance goals. It powered the F-89 Scorpion, the B-47 Stratojet in later variants, and numerous other aircraft, becoming a workhorse of the early Cold War Air Force. But the impact went far, far beyond one engine. The Vance effect, as some jokingly called it, though the official term became transonic compressor blade sweep, revolutionized axial flow compressor design worldwide. Every single high-performance jet engine built since, from the mightiest fighter engines to the massive turbofans powering commercial airliners, incorporates swept blades in its compressor stages. It is the fundamental key to achieving high pressure ratios, high efficiency, and stable operation at the near-sonic speeds inside the engine core. My design, rejected twice, dismissed as unsound and impossible, became utterly ubiquitous. The invisible heart-pumping air into almost every jet aircraft that flies today. I never became a household name like Whittle or von Ohain, but every time you hear the roar of a jet engine, every time a fighter pilot pushes the throttle forward with confidence, a little piece of that late-night struggle, that fight against dogma, that belief in a simple, elegant curve, is taking flight. They rejected my propeller design twice. Now it's standard on every U.S. jet, and the sky has never been the same.